Hello everyone, we are going to continue the Tectonic series today. But first I just want to say thank you everyone for being respectful on my videos and posting some very good points. I will try to address them if I can. I do forget suggestions sometimes. And, I want to stick to what I know a lot better than things I don't know. I do like learning new things, but sometimes it's too big of a chunk for me to do. And I'm trying to catch up on all the comments that I can. But earlier this week, on Wednesday, the 6th of November, we had to put a cat down. And she was 17. She was the one with one eye. It was Lilith, for those of you that knew who she was. And she was the last of my original three when I got out of the military. The other two passed, one in 2020 and one in 2021. So we still have cats. It's just, I've been very upset about it. I'll stop talking about it because I'm starting to choke up. And the last thing I want to do is clear my throat and snots while I'm talking to you. Anyway, we're going to move to the continents today. Sorry, still choked up. We're going to do the Midcontinent Rift. What is the Midcontinent Rift? The Midcontinent Rift is a failed rift system. It is not a failed rift arm, which is what we call an allocogen. What happens when magma upwells and hits the cold crust, doesn't matter if it's continental or ocean, you'll get upwellings, you'll get little holes in the crust, but eventually you're going to form a triple junction. Why? Well, if you sat there and added other triple junctions to it, this doesn't really happen, at least not on Earth. You would form a hexagonal shape. What happens with, like, basalts that cool quickly? You get columnar jointing, right? This pattern is something solids like to crack into, especially when there's a heat versus a cooler area variation. But they don't. They don't, because you only have one warming spot. So instead of breaking into six, they break into three. Instead of breaking into six arms, they break into three. And what happens is a rift forms. And this is looking down upon the surface. Sorry, I didn't say that. And what will happen is eventually one of those arms dies. That's an allocogen. All right? The Midcontinent Rift is a failed one of these. Our triple junctions, at least we think it is. We've been having a hard time finding this part, the failed junction. But most models seem to fit very well with like an East African rift situation. But anyway, so we have this, and the whole thing failed. So let's get back to Google Earth here. See, many of you may be familiar with the St. Lawrence Rift. That is an allocogen that's been reactivated due to continental stresses, but they're compensational. It's not like this is going to re-rift or anything like that. But this was the failed arm of this. And now we got a transform fault forming here too. So when this was a triple junction, this part was the St. Lawrence Rift. The Midcontinent Rift goes from Oklahoma up this way. You may be like, well, I don't know of it in Oklahoma. We'll get into that. Lake Superior, where it's exposed very well, under the Michigan Basin, okay, and down in Ohio. Now, I don't know if I agree with the interpretations here, but we'll talk about that here in a minute. But first, I want to show you what this thing actually looked like. This is another kind of view of an allocogen. Eventually, two arms will be preferred. We can't really predict necessarily which two will be, but two will be preferred. Let's get, we don't need that. Probably don't need that either. All right. This is what the Midcontinent Rift looks like. The reds here are volcanics. This is, where's the paper? Oh, we'll get into that. I think it might be behind it. I have to close it. But anyway, this is a paper. It's in geology a lot. I didn't ask you to grow. I wanted to go up or down. Anyway, doesn't matter. we've been doing kind of short, because a lot of geology papers don't need to be 30 pages. I write 30-page ones, but, you know, I'm a dummy. Anyway, most of the stuff can be done in a few pages, so GSA has started doing this, like, poster type layout, which is fine. It's just a layout. But here's our legend. If I can get it to drop down. This is really obnoxious. Anyway, let's go back first. I want to give you the source. All right. There we go. Midcontinent Rift Story Map. Okay, Communications and Publishing. Here's your source. Detailed description. All right. The actual paper. This isn't the actual paper. It was down here. But anyway, that's the title of it. You can look it up if you want. This is a slide. That's why it's not working right. But you have this here. And I can tell you from looking at this that the red and the greens are the volcanics. Volcanic rocks. Either intrusions or extrusions. I want to say the greens are the volcanic part and the reds are the plutons that came up. Now, this, you see this thing here, and here's basically two really large arms with maybe another one here. You know, it could be this is an arm connected to this arm. All right? But we don't see a third anomaly here. So it's probably one triple junction. We used to think it was this, you know, but it doesn't fit. The more we learned about these lava flows over here, oh yeah, that's another. These are surficial flows, so maybe these aren't just the plutons. This is the Duluth complex. It is complex, but these are surface flows as well. These are two. There's actually some down here, but I don't. For some reason, you can't see them. Anyway, and here's my area, my baby, up in here and up in here, and my cabin's up on this part, the Keweenaw Peninsula. But the purples are the sediments within, and that's mainly what I study, as a matter of fact. I've written papers about it. This is on ResearchGate, but the actual paper is in stratigraphy, which has a paywall behind it, and that's fine because they don't make a lot of money. They're not like Esri. They aren't these massive money makers. Okay, so this is it. The continent tried to split here 1.1 billion years ago with a B, it was Precambrian, and failed. Why? We thought we did know, but first let's go back to this. This is a gravity anomaly map, and I'll show you the paper in a second. You can see, yes, we can measure gravity anomalies, flat earthers. It's almost as if gravity is an actual thing. Wow, amazing, isn't it? You can see here. Sorry, I'm tired of flat earthers. All right, up here, you can see Lake Superior. It's hatched, and this is the Duluth complex, has a DC. And you can see it goes down to here. This is the exposure areas, basically around Lake Superior, the very northwest tip of Wisconsin. After that, it goes underground. And you might be like, well, how do we know it extends underground if all we have is gravity maps? How do we know it's not something else? So I didn't mean to say that snarkily. That is actually a legitimate question. Because we've drilled into it. They've actually drilled into it further than Kansas. So we've had to extend it. But then it's been drilled into over here too, in the Michigan Basin. Okay, there's these red clastic sediments with volcanics underneath. And the other gravity anomalies, this one here, this is something different. It's not what I used to think it was, because we actually have penetrated this finally with we have actual physical cores of this. Because everything not up here, basically from here north, is deeply buried. Okay, there's some exceptions like in Wisconsin, but generally that's the general rule. And you see this here, these gravity anomalies, which clearly indicate volcanism. And people do think this is a segment of the Midcontinent Rift. Some even say this is. But that would mean there's a massive fault here somewhere, and we don't see it. So is this part of the Midcontinent Rift? I don't know. There are classic sediments in it. It could be kind of like a compensational structure of the rift, and maybe not actually on the rift itself. It does seem to be the same age. They have drilled into this stuff too, and there was red clastic sediments on top of it. Let's see. Let's go. Let's close that, and here it is. Okay, if you want to look at it, that's where it is. And this was Stein et al. 2018. See, this is it. We used to think it stopped right here. And see, and now we know it goes into Oklahoma. And then you have this segment. And this does make logical sense in and of itself. You may be like, Steve, well, that doesn't look like a triple junction. That's because it's been compressed. We've had, since 1.1 billion years, this whole part here has been added. This was originally the continental margin. And people did hypothesize that this was the failed rift half of another half that was successful. But when we try to reconstruct the continents, and that was a great hypothesis. Stein also did that one, and I don't know if they're still pursuing it. I don't think they are, because in order for a bigger, like, say, Amazonia, I think, so the Amazon area, Brazil, basically, broke off of this, which was joined here at one time, you would have to move Amazonia out of the way while simultaneously merging the Grenville Front. Grenville Front's the core, the base, the oldest part of the Appalachians that predate the Appalachians of the Phanerozoic. Okay, that they're about 800 million years, 900 million years, somewhere in there, down to maybe about 7, but 800 million years for sure. There's just not enough space and enough time to do that. Okay, and plus, if you're rifting away, how are you also subducting in the same area? Then that's counterintuitive. It doesn't make sense. Okay, you'd have to come up with a more detailed, complicated model, which is possible. It's just, on face value, it doesn't seem very plausible. So I don't know if anyone's even continuing with it. So we're going to close that. We're going to maybe keep that open. I've done videos on this before, evolution of the Midcontinent rift. Okay, and actually, I think, so let's see if you can see certain features. All right, I'm going to talk a little bit about this. You see this ridge here? All right, my cabin's in this area. This way towards Lake Superior, you have volcanics covered with sediments. This ridge is volcanics. As a matter of fact, when it comes to single lava flows, I mean one magmatic event, not a culmination, not a group of lava sills, nothing like that. One eruption, the largest single lava flow on the planet, there's another contender, they're close, might be right here, okay, in the Midcontinent rift. There's something here, it's just informally called the greenstone flow, although it's about as green as the night sky. So greenstone doesn't have anything to do with color, but this is the ridge. It goes under Lake Superior and comes out over here, Isle Royale. So it's at least this big. All right, and this is a syncline here. This does form a syncline. It does not come out here. So let me try to draw you basically how it probably goes. All right, we don't know over here for sure because it's really buried. But even if it's just in these areas, like this, comes down to the Ashland and Superior synclines, comes out, it's buried under the clastics here, and then it's exposed up in the area by my home, comes out this way, and eventually gets buried. Even if this is the syncline, which would indicate a plunging syncline to the northeast, which is what we observe, Lake Superior is here for reasons other than the glaciers. And if there was a glacial lake that existed before the Quaternary glaciers came through, it was Lake Superior, at least in some form, because this is a Superior Basin. It's very old and it's very large, okay? It's not a carved out basin due to glaciers like Lake Michigan is, and Ontario, and Huron, and Erie, okay? This is a structural basin, all right? So it's at least that big. And we have what? It's on this scale, it's not very thick, but on a human scale, it's huge. Matter of fact, Michigan 26, you drive right through it. I've done a video where I take you to it. It's been a few years. Of course, it was in the middle of winter. So anyway, so we're at about 400-ish kilometers. Okay. All right. And that's just the edge. I mean, the volume would be contained herein. All right. And plus, some of it's eroded. We don't even know how much of it's eroded. It could be vastly more. But even at this minimum size, it's still one of the contenders for the largest lava flow on the planet. That's, for me, my, what do you call it? I don't even know what I'm writing anymore. My, Driftless Area book. Anyway, okay. Now here is a geologic map of North America. This is USGS. It's completely free, completely copyright free, so you can use it in any way, shape, or form you want. I actually put this on a t-shirt. But anyway, you can see here the geology, the bedrock geology. The glacial deposits are not on here. And one thing you notice, first off the bat when I do this, is the continent itself, to include the continental shelf, vastly different from the geology of the ocean basins. Compared to the continents, the ocean basins are very geologically simple structures. Okay? Geomorphology might disagree with me on that, but from a geologic standpoint, that is a true statement. Okay? You can just look at it here, and here's your rifts are the purple areas. And that's the East Pacific Rise down here, and that's Juan de Fuca getting eaten. Anyway, we're not focusing over there. We're focusing on the Great Lakes area, and I want you to look to, here is what a lot of people know as the Canadian Shield, which is also known as what craton? Oh, Steve, this Canadian Shield's fine. Shield and craton are pretty much synonyms. I mean, geologists use them interchangeably. It's not a big deal. The superior craton's down here. Okay. Now, you look at this geology, and it looks vastly different than known plate tectonic margins, doesn't it? Here, this was a compression area that later rifted. Here's our Grenville. This is what we're talking about when we say Grenville front. It is, where's Sudbury? Where are you, Sudbury? Okay, here's the Grenville front. This is the modern Appalachians, well, modern compared to Precambrian. And this is your Grenville front, which comes down here, underlies the Appalachian Basin, which is this, and comes down and eventually meets up with it or peters out, because when the Grenville front collided with North America, basically everything south of Illinois wasn't there. All right, that stuff came later. Now you look over here and you look at typical plate tectonic features. You see mountains, you see these ridges, these crumpled ripples. Now this is the basin and range. We're getting extension, so it looks different. But even here you have the Colorado Plateau and other things like that, kind of reminiscent, or not reminiscent, but kind of definable plate tectonic features. You look at the Canadian Shield, you don't see that. These are alternating greenstones, if you will, intruded with plutonic granitoids, and most of them are Archean. The patterns are distinctly different from the patterns over here and the patterns over here. Okay, now there is slabs of ocean crust thrown up here. Matter of fact, there's one right here in Wisconsin. Talk for another time. But this is completely different. And that's why we don't think plate tectonics was an operation then. Okay, and the Hudson Bay is there for a couple reasons too, like Lake Superior. It is there because of the glaciers, but you could see some Phanerozoic. These blues are Phanerozoic sediments that were posited on top of it, because this basically was how the Michigan Basin would have been if it was still having sediments deposited in it, which is a large, bigger scale. All right, so Midcontinent Rift. So I'm giving you guys way too much information here. I apologize. You can see these orange rocks and these red rocks marked X, X is Proterozoic, W is Archean, Y is Neoproterozoic. Okay? X is Paleoproterozoic. Y is Mesoproterozoic. I'm sorry. Z would be Neoproterozoic, but we don't have any of that up here. Well, we do, but there's still some old geologists who will deny it, but we have taken detrital zircons from the Jacobsville group of rocks, which I redefined almost 10 years ago now. And the youngest zircons are about 900 million years old. And in sedimentary rocks, obviously the zircons did not form there. They were brought there as detritus. But you can't include something that doesn't exist. So 900 million years, if there's a zircon that young in the Jacobsville has to be that age or younger. It cannot be older. That's just how the physical world works. You can't include something that doesn't exist. All right? That's how reality works. All right? But anyway, that aside, W is Archean, okay? We're not going to talk about what U is and all that stuff. Those are also Archean. U, V, W, X, Y, and Z are kind of the archaic way when we knew rocks were related to one another and around the same age, but we didn't have any radiometric dates, and now they're held over for geologic mapping, which is fine. I don't have a problem with that, and that's what these little superscripts are. They're subdivisions of those. X1 would be the youngest Paleoproterozoic, X2 the middle, X3 the youngest, although the Paleoproterozoic is divided into more than 3 parts. Anyway, I digress. Here we go. Okay, basically anything Y here you see is the Midcontinent Rift. And you see here, this is the edge of the Michigan Basin. So these rocks were deposited after the rift. This is all Phanerozoic. So it's Cambrian or younger. And same thing with Illinois at the surface. It's Cambrian or younger. That doesn't include the subsurface. Same thing here. You can see here, and obviously we have some Precambrian outcrops. Down there, here's the Baraboo, stuff like that. But it disappears here too. Why? Because we have another basin. And then it continues in the subsurface, and you saw those gravity anomaly maps all the way down to Oklahoma. And it probably influenced some of these basins, how they formed, because it's older than all of them. Right? It's older than the mid-New Madrid Rift system. It's older than all of this stuff. All right? And the continent basically ended in northern Oklahoma. So the rift, obviously, we're never gonna find the rift down here because this didn't exist then. Okay? And you could even see that on the gravity anomaly maps. So here's where it is. All right? And that's also the Superior Basin. So basically, what went on? What happened here? All right. Well, we had a weak zone, like I showed you. We probably had a triple junction. And magma started to rise up. Eventually, an arm died because subduction was happening somewhere else. And we're not exactly sure where, because all that ocean crust from 1.1 billion years ago is gone. It no longer exists. So the margin of the continent at the time, now, it doesn't mean North America was smaller, because it's experienced numerous compression events like the Grenville and stuff like that. But when the Midcontinent Rift formed, basically, let's go. This was the southern margin of what we call Paleo North America, or Laurentia. None of this existed either. All right. This is just me roughly doing this from memory. This is not exact. So this existed. This did not. This is all accretionary terrains or continental margin sediments that have subsequently formed, or since then. And our rift came down like this, up like this, probably down like this. Okay. And this isn't exactly right either, because it should be more over here because of the Grenville front. So let's actually do that. Let's do pre-Grenville, okay, collision, because that's easier to do. So this would be it pre-Grenville. That's Yellowstone. We do have older Precambrian rocks here. We'll just do that. Okay. And it probably might extend this way. Matter of fact, I think it does. It's just, okay. This is just the best I can do from memory. So this part was Laurentia. This didn't exist, or existed as blocks elsewhere, cratonic margins elsewhere. Okay, so this is what the coast roughly of North America would have looked like before the Grenville front, before the Grenville came as an accretionary terrain, okay? That's what it would have looked like. All right, so just to give you a picture of that there. So everything up here already existed. And then, if we do another one, let's try to do this here. So our Midcontinent rift, I don't even know if this is going to work. Nope, it's not. Ignore that big 45-degree angle line. Okay, we're just going to pretend that's not there. It's roughly something like this. So you can see it came to the edge of the continent before the Grenville came. And then that would be this mess. Ignore that line. It would be this, about this mess here. Okay. So our rift, let me clear this and bring it back. So this is, oh wait, no, that's incorrect. Sorry. I keep forgetting how much it bends back under the Michigan Basin. It's due to compression that it looks this way now. Otherwise, it's not more like a textbook rift. All right, so there we are. There's a Midcontinent rift. Okay, and that's where it looks. That's where it sits on Earth. All right, and for whatever reason, we used to think the Grenville is what shut this off, because that does happen. I've told you before, you can get rifts that get consumed under subduction zones. We see that happening right here with the East Pacific Rise. Okay, let's see. This is getting subducted. Okay. So we know, but this is a continental rift, so it wouldn't have gotten subducted. Best that could have happened is it got shut off. And the timing is right. That kind of does make sense. And I believe actually the Grenville, some segments of the Grenville might actually be closer to 1 billion years old. Please look that up if you're interested. I don't have everything memorized, guys. But 800 million is about when it stopped. It's not younger than that. And that is pretty much, yeah, that's true. Okay. And it's actually a bunch of segments. I'm just saying, using it as a general term for every collision over here from 1 billion to 800 million years ago. Okay. So that caused compression and the rift to die. So we thought. But with the way we have lips, large igneous provinces laid out around here in this area and other places, we're not so sure that's what happened. The shut-off mechanism, being the Grenville front, is an idea from maybe the 70s, late 60s, mid 70s, somewhere in there, right after plate tectonics became accepted as a theory. This concept came into being. And it's no coincidence either that this got recognized as a rift shortly after that. Because before plate tectonics, they didn't know what to do with this. They just saw this massive volcanics in the middle of North America that they saw nowhere else in North America, or really anywhere else in the world. This is the largest failed rift system on the planet. This is it, right here. That is true, okay? So it was out of place, and they gave it some funky names. It was even called the superior anomaly, just stuff like that, or the Midcontinent disturbance. They used to attach disturbance to a lot of things that they didn't understand. Cryptovolcanic was another. thing that ended up being largely meteorite impacts. I knew this was not a meteorite impact. It could not have been. So they stuck with disturbance more often than not. But there's meteorite impacts we still call disturbances to this day, such as the Des Plaines in northeastern Illinois, which is deeply buried under the glacial stuff. Anyway, so that's all I want to tell you guys, I think, about the Midcontinent Rift and how it's very weird and unique. And at about 1 billion years ago, no one questions whether or not plate tectonics was in operation. It's weird. We have the old timers who think plate tectonics goes back to frickin' before the Earth formed. Obviously not that far, but since day one. And that's not what we observe in the geologic record. Then you got some people who believe modern plate tectonics was about 1 billion years ago. The breakup of the supercontinent before Pangea. Remember, we've had supercontinents before Pangea. Okay, that one was called Rodinia. Okay? Now, Rodinia existed shortly after the Midcontinent Rift failed. Okay? Obviously, Grenville here. But even though it was a supercontinent, we are getting really good at reconstructing that one. And if you guys are interested in just the Midcontinent Rift, stop watching here. Okay? Why? Because I'm going to talk about how we date, not date, but how we know where the continental regiments were if we have no ocean crust. Now, I know geophysics people who went to Michigan Tech. It's like right in Houghton, and great French and Finnish people. Okay, Houghton right there. And we would go down to Marquette, and I did the detailed geologic map of this island over here. Little Presque Isle. There's so many Presque Isles in the Upper Peninsula. Anyway, this is Little Presque Isle. Okay? Alright. Let's see. Where is the distance between... And I'll tell you how we get to it. Let's use meters. I can change it. At present, you have a distance of 159 meters between the mainland and the island, which is about 524 feet. That wasn't always it. You can see the bottom in this picture. This used to be connected by a big sandbar, and there are pictures out there that show that. All right? But this is a very dynamic part of Lake Superior. And this little inlet here is here because of the geology of this. Not the geology of this right here, but because of this. But anyway, we would go here, and the geologic map's available on the Midwest Institute of Geoscience and Engineering's website. And even on the crappy, see if we got a better looking one. Yeah, here we go. Yeah, the 2019 one's better because it's after the leaves fall. Because remember, or it's in May. There's still very little greenage in May. You see this? This is a dike. That's a wide dike too. That's one of, and it's Keweenaw age, meaning Midcontinent Rift. You know, almost 40 feet, about 12 meters in diameter. Okay, and it runs under here, and on top you've got Jacobsville sandstone covering it. But you come down, that's been sampled. There is another one, and it's a picture I have. It's right under this here. You can't see it, but it's a dike showing columnar jointing. This expresses columnar jointing as well. These dikes are basalts, but they're intrusive. These are not extrusive basalts. They intrude Archean, Compo, gneiss, granitoids. Okay, there are blacks here that are not Keweenaw, but there's all kinds of Keweenaw dikes here. Here's another one. Okay, there actually are lamprifiers that have been dated that go back to the Panokian, so 800 million years before this, down here. Okay, if you want to, actually, nah, I'm not going to show you a geologic map, but, you know, whatever. What we do is we take geophysical samples from these things, these basalts, okay? We have to keep their orientation on the planet written on them so we know where they were, how they were oriented, and we can run geochronology on those the same way we would on the ocean floor. And that will tell us, assuming we had a dipole situation, that the same information the ocean basin tells you. It will put you where that little island was when that basalt intruded it. Okay? So when that basalt, 1 billion years ago, about, intruded this Archean compo gneiss, we take that and we can tell you on the planet where that was. I forget exactly where it was 1 billion years ago. I think it was nearer middle latitudes. I could be wrong on that. I forget where the paleopath is. And that's how we know there was a dipole situation. We can pick out magnetic reversals just like we can in the ocean crust. Okay? Because the Midcontinent rift, there was a reversal during the deposition of Midcontinent rift. The volcanics basically go from 1.12 billion with a B to, we have some as young as 0.9 billion or 900 million years old. So it's not a very large amount of time. But in that amount of time, the pole flipped. So we get that too. Matter of fact, that little mountain up here, wait, where is it? Little mountain. And there's a lot of geologists that disagree with me on the interpretation, but I think it's pretty obvious about how this thing formed. All right, we go here. Are you going to go? Why? Oh, I think it's because that's open. Oh, come on. And it locked up on me. Fan-effing-tastic. Is this at least still recording? Yeah, okay, we are. All right. Anyway, little mountain somewhere over here, and it's surrounded by swamp, glacial stuff, and it's a piece of bedrock that sticks out. All right, and that bedrock is what we call the Michigami Formation. It's metasedimentary. And in there are two dikes on the very top that crisscross each other. Both are Keweenaw. They're really close to each other in age. Matter of fact, the margin of error, if I remember correctly, overlaps. But one's normal polarity and one's reversed. So we know we could, because of those two dikes, we can get really, really close to, it's just, yeah, screw that. I'm not gonna, all right, really close to when that reversal happened, even though it was over 1 billion years ago. It all depends on how well this stuff is preserved. So that's how we get continental arrangements pre-Pangea, okay? We rely on lips, large igneous provinces, and they have to be undisturbed because otherwise you'll get metamorphic overprints. And the Keweenaws are surprisingly not disturbed for being compressed. Well, a lot of these dikes are post-Grenville or near the end of most of the Grenville accreting. So most of the deformation had already taken place when a lot of these lips popped up. So, but I think that's enough, guys. That was really long. If you have any questions or comments, please leave them below. And I hope you guys learned something.